Good afternoon, everyone. My name is Carl Wunderlich. I'm the director of the Noblis Autonomous Systems Research Center. I'd like to welcome everybody to join us here for our Systems of Autonomous Machines Challenges and Opportunities, our all-virtual event. Well, except for Chris and I, we're not virtual. We're here live from the lab. To get started, I'd like to turn it over to Chris, our Chief Technology Officer, who's going to tell us a little bit more about the event and do the official welcome for today's event.
Again, thank you everybody for tuning in today. It's really exciting to host this event from our lab here in Reston, Virginia. This is an extremely exciting domain area for us and really for the federal government and really across industry. So we're excited to get things kicked off. As a leading science and technology provider of expertise and capabilities to the federal government, we have a bit of a bird's eye view here at Noblis into what's going on into the autonomous system space. And there's a few things that we can take away and share our worldview. First, there's an enormous amount of energy in and around autonomous systems. The adoption of the technology is really accelerating. You're really seeing a lot of questions being asked about how AS can be applied to the battlefield space, to sea, to federal civilian air traffic management and terrestrial transportation, our cities and highways. So really a lot of new things coming and a lot of discussions being had. You're also seeing, of course, with the prototypes coming available and into the field, a lot of operational constraints, challenges, et cetera, to overcome. These include challenges to trust, communications, security, and everything in between. So we're here really at the nexus to help identify those and get through some of those challenges together. Those get exacerbated by when you think about scale. So it's one thing to run a drone or two, right, in your backyard or in an operational environment. Whole different situation where you're dealing with drones at scale, UAS at scale, et cetera, particularly in a mixed kind of environment between air and terrestrial devices. So that's causing some really interesting challenges. And finally, you really have the issue of, for the foreseeable future, a personed, a semi-autonomous, and a fully autonomous multi-mode environment, where you're going to be seeing vehicles, technologies, in all of those three different areas interacting together. So again, that brings up a whole slew of new challenges on the policy front, on the technology, and the interoperability front that we're working through together. So these and other topics are some that we'll cover today in our discussion and through our panel. So just a quick, couple quick comments about Noblis. We really are at the nexus of innovation and capability development for the federal government. Now, we're here talking about, of course, our Autonomous Systems Center and some of the work coming out of our lab and really some of the work across the federal agencies that's being done. But our capabilities really span multiple different areas through our research centers, through our labs here in Reston and elsewhere. I encourage you to look at our website, noblis.org, really get a feel for our capabilities and the work that we're doing. And some of these other domains that interest you, by all means, please let us know. We'd love to talk to you more about them. I think when you look at our span of capabilities, it's best to look at them in two different dimensions. One, we've been a partner in the federal government for program management operations, federal acquisitions, driving those to success, systems engineering, and digital transformation for many, many years. Similarly, when you look at our scientific and technical capabilities, each led by one or more senior technology or scientific experts, I think one of the things you can take away is not just the depth and the breadth, but one of the things that makes Noblis special is our ability to bring together the best experts in their fields to really drive solutions and identify solutions to our customers. We invest very heavily in our employees' professional development and very heavily in our research, into our internal research and development program. All of these, I think, result and speak to Noblis being one of the top-rated workplaces by the Washington Post and being one of the top-rated, most ethical companies in the world. I will, if I can, Carl, we are always looking for the opportunity to onboard exceptional senior scientific, technical, and talent. And as you peruse, listen to today, if yourself or your colleagues are interested, by all means, stay with us. We'd love to hear from you there. So why are we sponsoring this event? Well, it goes back to what I said earlier. We're really kind of at the nexus of a lot of what the agencies and the departments are going through. We hear a lot of their stories and challenges. It's always great to get people together from various mission sets, domain areas, kind of work through those together. Right? There's a lot that's going on in the military that I think is of interest to share with the federal civilian space and vice versa. So today's session is really about talking about collaboration, ideas, things to get us through and foster adoption safely of autonomous systems for the betterment of our missions and the public and our national security. So today's agenda, I'll be passing the baton over to my friend and colleague, Wunderlich, in just a moment. We'll have a series of tech talks and quick demonstrations. We'll then get into our distinguished panel, which we're really excited about, featuring Kate, Andy, Greg, and Con. So they'll get a chance, of course, to introduce themselves later. But again, I just want to close welcoming everyone to today's session. Looking forward to some great discussion and dialogue. And Carl?
Terrific. Awesome. Thanks, Chris. So as part of our agenda, as Chris pointed out, we work at the connection of so many different federal clients. And so we're going to talk a little bit today on autonomy and autonomous systems, particularly our worldview, as Chris was talking about, what happens when these autonomous machines get deployed at scale. They're taken out of the lab and go out there into the field and really transform agency missions. So the first segment that we're going to talk about today before we bring out the panel is to first illustrate some of the things that we've encountered in our research that we think are fundamental elements, fundamental challenges, fundamental opportunities around the notion of deploying autonomous systems at scale to solve agency missions. So to do that, I'll be joined by two colleagues, James O'Hara, who's the manager of this beautiful lab that Chris and I are broadcasting live from today, as well as Dr. Mohammed Gholi, who is our robotics lead in our lab here at the Research Center. So first, I'm going to give a little bit of insight about how we view the world of autonomous systems, more specifically, the challenges and opportunities that we see here from our vantage point, try to describe that. And then I'll turn it over to James and Mohammed, who have some demonstrations they put together that illustrate some of these key challenges that I'll cover. All right. So first, I'd like to level set a little bit on what we consider an autonomous system. So here, I think the critical thing to know is that having a machine, an autonomous machine, a rover, a drone, a submersible, or a float platform, and performing actions and missions that had been previously assigned to manned systems is a very interesting problem in and of itself. And there's lots of great stuff that we could talk about just in terms of autonomy there. But when you talk about moving out of the lab, and instead of searching, for example, a small space, and starts searching something very large, like the ocean, then you're going to need to have the ability to scale up those capabilities. So another critical component is that the real world, unlike a lab, has a lot of other entities in it. Some of them are humans, and some of them are other machines, either unmanned or partially autonomous, as Chris alluded to before. So the environment is almost never as clean or as simple as a lab environment might propose it to be when you're doing those first tests. And so for us, this notion of many machines at scale is not just strictly one kind of rover, one kind of drone, one kind of submersible, multiplied by 1 million and throw them in the water or into service. Because the real world out there has a bunch of other machines in it too. Automated vehicles, drones, submersibles, float platforms, and rovers. And it's very likely that those machines are going to interact with other machines that are unlike it, as well as with humans who may or may not be aware of the presence or the mission that those machines are performing. So we use this term machine broadly and conceptually throughout the day today to illustrate this heterogeneity component, that we predict an autonomous system in the future to be one with many machines of very different types, very different capabilities, sizes, weights, and trust. And trust, we'll talk about it in a minute. But altogether, an autonomous system is not just merely 3 rovers deployed together that can do simple actions and stay out of each other's way. An autonomous system to us is a self-organizing system which contains many heterogeneous and connected machines, all potentially working together, or at least trying not to get in each other's ways and operating safely throughout. Okay, so a clear goal for us is not just to create an autonomous system by collecting up autonomous machines and throwing them together and seeing what happens, but to create autonomous systems that are reconfigurable, resilient, that can self-organize dynamically based on the conditions that they encounter. I mean, no plan survives first contact with the enemy, right? And whether that's a traffic signal plan on a roadway system or actually in the battle space. So the ability for these systems to adapt is critical. And I'm not going to walk you through some of the elements of why we think these autonomous systems are indeed transformative and super powerful for our federal agencies in many different domains. The first is, again, as I point out, is that there's going to be a lot of heterogeneity in the system. And that's a strength. That should be a strength and can be leveraged as a strength throughout. Different machines, different capabilities, and different value, right? So a drone, which is a couple $100 versus a large platform, which may be several $1 million, you want to have different risk profiles for those particular things. And that's not just on the military side, too. Similarly, if you have on the civilian sector, that same drone looking and searching for something, there may be a much more expensive recovery machine, which is used to clear, for example, traffic or deal with a hazmat spill. So these autonomous assets should be considered together as a self-organizing system. And even if those machines can't always talk to everybody in the group. So we're not trying to deliver a monolithic worldwide capability of autonomous systems. So these machines should be able to organize themselves based on who they see around them in ad hoc and powerful ways. Finally, this other point I wanted to make about highest value assets is that they self-organize with a sense of what the value of the individual elements are, those machines, so that the appropriate machine with the appropriate capability, with the appropriate risk profile can be committed at any particular time. All right, which leads me to a critical point. In order for all of this to work together, one of the things that we have spent some time on and we think is critical as an insight broadly for autonomous systems like we've just talked about is that there has to be a way of managing trust over time. So if you have a mechanism that says we've been assigning machines to do certain actions or to maneuver in a certain way, if you don't have a way of measuring how they perform against that, then you have a tough time managing risk across the entire system. And so later on, James in particular, in his demonstrations, could talk a little bit more about how we quantify and utilize trust. But this is a critical component. Without a system that includes a form of trust, there is no way to be effective in the kind of reconfigurable, resilient, autonomous system that I've just described. So another point to make is that although the system is self-organizing, it doesn't exist for its own, just for its own sake. It's there to perform some human-derived action, and humans are still part of the system. And so there's a mechanism that we have to think about with these autonomous systems about what is the appropriate level of control or influence that any particular person should use or can use as a controller or just interacting with the system. And then finally, if all this pulls together, this is like the end of our worldview, if you have these multiple configurable autonomous machines working as a self-organizing autonomous system, then you've released some incredible power in all sorts of domains. Okay, so why do we have this? Why do we have this worldview, and where did it come from? So I would be remiss if I didn't point out that we've been working on this as a research area over the last 4 years, developing this worldview that I've just described to you. And in fact, just a couple months ago in March, this worldview was rewarded with a patent by the U.S. Patent Office for its innovation. I only use it here to illustrate. This is to provide a base to see where we come from in this space and why we view it the way we do. Because the patent itself is a mechanism for understanding how we see an autonomous system and both the challenges and the opportunities to making it a success. So around this diagram, I won't try to brief every part to it, part of this to you, because it is quite complicated. But what I will say in a couple of clicks here is that, first off, there are ways that we use to identify what machines are nearby, this proximity boundary, what machines need to interact with each other. We have a number of innovative ways that we help the machines to self-organize. It's not the only way of doing this, but this is one way that we have innovated to do it. And then second, there's a way of, we look at in terms of sensor and intent sharing. So once those machines form a group, then they have to also share information with one another, as well as their intent, where they plan to do, in terms of where they would go and what the actions that they will take. Again, trust is important in the collective map generation. Bahama's going to talk a little bit more about that. How they plan maneuvers and actions. How they verify, actually, the motions and the actions and how successful those things are in the teams that they have formulated or in the ad hoc collections of machines that have been formulated. So this is an important feedback, because if there is no mechanism by which we say, well, that machine actually did perform the maneuver or did not perform the maneuver, then there is no trust in the system. So verification is an important component of it. The management of trust has been a big focus for us, how those verification reports are turned into multidimensional array values that influence future planning, and managing dual communications. Another critical component here is that when people say, well, how do you do all this quickly enough? We have an important decision to make about identifying what needs to operate in a fast-moving space and in a slow-moving space. Finally, as part of our innovation, we demonstrate how blockchain or distributed ledger technology can be utilized to help this function, the whole system function, in a decentralized way. Okay. So why did I tell you about that? I tell you about it because that's where we have been living for the last 3 or 4 years in our worldview about trying to reach forward towards a specific type of autonomous system that, as I pointed out before, is resilient, reconfigurable, has ad hoc components, and has the ability for humans to step in and out of control of that system at various levels to achieve the mission. Okay. So now we could try, what's hard to do is to demonstrate how this works with 1 million machines, right? That's hard to do, but what we can do, and what we're going to move into now, is some demonstrations conducted primarily here in this lab environment, not live today, but in a previous session, where we illustrate some of these critical components of what I just talked about. Now, we're going to use some relatively simple machines to do so, some rovers and drones, but I'd like you to imagine, depending on what is your use case of interest, these rovers and drones doing things maybe as different kinds of machines. They are essentially conceptual stand-ins for any of the kinds of autonomous machines that I talked about earlier on in my presentation. But with that, I'm just going to give you a quick lineup of how it's going to roll out. First, we're going to talk a little bit about machine orchestration. James O'Hara will lead that, including diving a little deeper on why we think trust is so important and why trust, in terms of machine trust, differs from human trust. And then Dr. Goli will take over to do a next demo, which shows how machines that perceive the world differently from each other, based on their sensor arrays, based on their ability to maneuver, how they can generate a shared situational awareness by collectively providing a map. And then last, James has some very good and interesting observations to make based on some of our attempts to allow the humans to interact with these machines at very different levels, depending on what's required. All sort of couched in terms of what are these challenges, and if we can overcome these challenges, what will be the benefit in terms of transformational capability. All right. So with that, I see my time is about up. So I would invite James O'Hara, I believe, James has the first one here. James, if you can hear the sound of my voice coming to us from a remote location, not in the lab today, please take over and you can show us the demo.
All right, thank you, Carl. Yeah, so as Carl said, our first demo is the collective maneuver planning and earn trust demonstration. So the first part of these are 3-part videos. So this is a little bit of context to set it up. The first 2 will use our 2 small, fully autonomous rovers. In this case, they'll have conflicting goal points. So you see in the image in the bottom left, rover A in yellow. The yellow rover you'll see in the video is trying to go from the top down to the bottom point, while rover B, the one in blue, is trying to go straight across from right to left. This creates an issue where if there's no communication between rovers, in this case, in our isolated autonomy, they can only use their infrared sensors to perceive the world around them. So they have 8 infrared sensors around their top. They use that to identify obstacles and stop and try to change their path to move around them. But since there's no communication, as you see in the image on the right, as they both move towards the center following the ideal path to their goal point, they'll both meet in the middle, and they have no way of knowing what they're going to do next. So with that, we'll get started with our first video. So this will be a top-down view you'll see of our 2 rovers. As you see, the yellow rover begins moving to its goal point, as does the blue rover. And at the last second, the blue rover is able to identify that there's an obstacle in its way. So like you can see, isolated autonomous systems, they can work very effectively. You have these sensors, they have a lot of code in them to make sure they work safely and they don't collide. However, one of the issues we really see is in a lot of these cases, like right there, where they have to move in very close quarters, make tight maneuvering, and trying to do that based on only the information they have is very difficult. So in that case, the blue and the yellow rover were trying to go basically to the goal point that the other one was occupying at the time. That means they're moving right into each other. There's a lot of wasted time. There was a small collision, as you saw, and then there was a lot of wasted time where they both were right next to each other and had to figure out, well, how do I get around this giant obstacle that's right next to me, let alone having to then deal with the fact that that obstacle is trying to also do the same thing. So in some of these cases, you can see there are a lot of benefits to isolated autonomous operations. There's a lot of time where you'll be able to see that your autonomous decision engine is working correctly. It's following the path that it's setting out correctly. It's seeing obstacles. It's not hitting them. It's avoiding them. And in some of these cases, you can see like right here, where they're again in close maneuver, they're able to actually work around each other without an incident like before. And the blue rover is able to get to its goal point while the yellow rover is getting to its goal point. And so you might say, if you're testing out autonomous decision engines, 1,000 times it might do that maneuver it did down there 1,000 of those times and get it right every time. And then the 1,000th first time is when all of a sudden there is a collision. It's so difficult to build an autonomous decision engine that can account for every single situation that you're going to encounter, especially in a real world environment, and not just this laboratory conditions like we have here. So again, you can see this is another case where the yellow and the blue rover are close together. The yellow rover made a small collision and is now having difficulty maneuvering around the blue rover. And one of the other problems we see with this is not just like a safety concern where they're colliding, but an inefficiency of movement, because now the blue rover is stuck because it had the yellow rover in front of it. It doesn't know that that yellow rover was a moving obstacle. It just knows it was in the way. And now it needs to sit and wait until its sensors can confirm safely that there is no longer an obstacle in its way. And by sitting there now, it's getting right in the way of our yellow rover, which has collided again. So those are some of the main issues that we see with isolated autonomy. It's difficult to program for every potential situation. Sensors can present inaccurate or incomplete information, and if you're relying only on your own, you can't share information. You have to work on that inaccurate and incomplete information to make decisions. Close-in maneuvers can lead to collision, even with safety buffers and low speeds. You can't account for every single time. So that's why you have to travel at those low speeds, because if you have that collision, you could hopefully be a safe collision, but that then leads to a lot of inefficient and wasted and slower movement than necessary trying to navigate around these unexpected obstacles. So our second demonstration that we have here is Noblis's patented orchestrated autonomy, standing in for the idea of just general autonomous machine teaming and the benefits that we see from it. So in this case, it'll be the same the yellow and the blue rover in the same constrained space as they were before. But in this case, the machines will communicate their identity, their position, and their intent. By what we mean by intent is their planned path every 5 seconds. They'll send that, And then if they change their path for any reason between every 5 seconds, they'll send out an instant path to notify the other vehicle what change has been made. When they do that, they then coordinate their action, and one vehicle will give the other one priority in space and time if they're trying to go for the same spot. So again, you see in the bottom left, the same image as before, where A and B are going to try to both cross through the middle, following their ideal path to their goal points. But on the right, in this case, we can see that they've negotiated that from time 0 to 5, the blue rover and the yellow rover are safe in those first 2 green spots. But then the yellow rover will stay there for the next 5 seconds while the blue rover has priority to move through the space and then gets to its goal point. The yellow rover then will get to its goal point later on as space is cleared out and moved. That way you prevent those conflicts. So this is our orchestrated autonomy demo. Again, we have the same top-down view. You'll see that the yellow and the blue rover both start moving until they have that communication. You see the yellow rover then stops and moves away from the conflicted space, allowing the blue rover to immediately get across to its goal point. In this case, again, they're going back. They're going to both try to go to the same goal point in the bottom. That communication allows the blue rover to play priority for the goal point. And since it's occupied, the yellow rover switches goals and moves up to the one at the top instead. So in that way, it knows that instead of having that inefficient movement of going all the way down to the bottom of the screen, the left of the screen, before realizing that the blue rover was also going there, it knew way earlier, was able to adjust and find a different goal point and achieve its objective. You can see in this case that they're now trading off. Again, the blue rover pays for priority. The yellow rover switches goal points. There's a lot fewer close-in maneuvers because they're having this communication and they know that the other rover is going to be there, and they don't have to work, they don't have to get so close to realize where the other vehicle is. The real backbone of this, though, as Carl mentioned earlier, is trust. These 2 vehicles, if they were to work just with simple binary trust, it'd be very difficult. In a binary trust, either you trust everybody or you trust nobody. If you trust everybody, every information you're told, that can present a serious cybersecurity risk. If you trust none of the information you're told, you're just working in isolated autonomy. So you need some way with a granularity to understand the differences between autonomous decision engines and how much you can trust the information they're telling you and how well they can follow through with it. So in Noblis's patented orchestrated autonomy system, the way we do that is using a distributed ledger and peer reports. So as the blue and the yellow rover are working through this space and interacting with each other and coordinating their actions, they're also rating each other on how well they are following the plans that they've come up with. So in these cases, when the blue rover is asking for priority in the space at the bottom, the yellow rover is then rating it on how well it's using that space. So in this case, the blue rover did follow the path it planned to, so the yellow rover would give it a positive rating. In the future, in some cases, if the blue rover asked for priority, but then didn't actually use the space and the amount of time expected, the yellow rover could give it a negative rating for that time. And so in that case, with those ratings adding up, you can then have a ledger for each vehicle with all of its individual peer reports that can be combined into a single score that can tell you the trustworthiness of a vehicle. So then we could introduce an unfamiliar machine to these 2 autonomous robots that's also operating in the same space autonomously, and it would instantly know how trustworthy the information that the blue and the yellow rover were giving it based on that peer reports that they've been giving each other throughout this demonstration that we've seen. And in that way, it can make better decisions based on the information it's being shared with. It can see obstacles better. It can know where the vehicles are going. It can move. As they increase their trust, they can move slightly closer together. They can move a little bit faster because they know that they can trust when a vehicle tells them that they're going to be in a specific point at a specific time, that will be true. So overall, as you can see, this is a lot better than we're seeing from the isolated vehicles as they're having that distance between them. And not really, we haven't seen any collisions yet. We haven't even seen very many close-in maneuvers. So in summary, our coordinated action increases the overall network efficiency and safety. As you can see that video, even though when there are times when an individual vehicle was taking a slightly less efficient route for a brief period of time by giving up priority in the space, overall, they are getting to their goal points a lot more frequently and a lot more quickly. and a lot more safely, as we didn't have collisions as we had in the isolated autonomy example. The machines giving up the priority, like I said, they temporarily follow less efficient paths, but overall they move more efficiently in the space and time. And then we have that backbone of trust. The efficiency and the safety improve as the trust increases over time. And as I said before, if you were to bring in an unfamiliar machine that never interacted with those two vehicles before, it would still know how trustworthy the information is being shared with it based on those trust scores that had been built up and earned by these two vehicles previously. And so our final part of this is our multimodal machine teaming. So the first two examples, we're using our ground rovers, but as Carl said before, these are really just a stand-in for any sort of vehicle you can see. And one of the other benefits you can see with autonomous machine teaming and orchestrated autonomy in specific is that it does not need to work with a specific mode. It can work across modes of mobility. So for this example, we're going to use a drone and a ground worker working ground rover working cooperatively to collect an object of interest. So the drone will be able to fly over obstacles and use its camera to locate the object of interest, while the ground rover will be able to use its arm to be able to drive around and pick up the object of interest to take it to a neutral location. The common language of autonomous machine teaming allows for communication and sharing across the two different modalities, and you'll see the machines coordinate the task allocation to the most. So you can see the drone is taken off on the right side of the screen, is able to fly above the obstacles and localize the object of interest. It then takes that location and is able to share it to the ground rover as they share common mapping and understanding of the environment. The ground rover is then able to autonomously maneuver through the boxes presented as obstacles to it and is able to drive around them and get to the can. And then it can use its arm to pick up the object of interest once it's able to identify it with its camera. All of this is being done fully autonomously. All of this is being done by the drone and the rover assigning themselves tasks and sharing information with each other. The only thing that we did is before the demo was set was to tell them that the mission was to identify this object of interest and pick it up. And they were able to fully autonomously, as a team, complete that mission together without any additional input from us. So with that summary, orchestrated autonomy, as you can see, applies across modalities and competitive and cooperative missions. In our first two examples, those vehicles were working competitively to try to get to their goal points as quickly as possible in a shared space, but were able to coordinate still by using orchestrated autonomy. In our last case, it was a cooperative mission, but they still used the same principles to succeed. And a team of heterogeneous autonomous machines can coordinate to accomplish missions that would be difficult for a single machine to do. Our drone and our rover there, they can bring different aspects of, different positives to the team, but they wouldn't be able to accomplish all of that on their own as successfully as they can together. And with that, Carl, I'll pass it back to you.
Great, thank you, James. I think we had a little dramatic music in the background there, a little bit. That's for but we can still hear you well, I believe. All right, so so that was James's demonstration. I think hopefully everyone got from the takeaway there is that you can't have priority without trust, and without priority, you don't have the capability to do any sort of self-organization, or intent sharing itself becomes a moot point, right? So we kind of jumped ahead to some critical components related to why we think trust is important. But trust also influences not only how maneuver plans are generated and where they go, but also how much we trust and how we integrate maps from multiple kinds of machines. So in this particular case, we're going to throw it to Mohammed. In James's demonstration, we kind of done all the mapping already in those demonstrations. Now we're going to take a step back to talk about this important step, which is how do you generate a map and then utilize that map for multiple machines to utilize in a space where an available map can be drawn by the machines that are together, rather than from some third party. So with that, I'll invite my colleague, Mohammed Gholi, to take the screen. Mohammed, if you're out there.
Sure.
Alan, can you hear us?
Yes, can you hear me loud and clear?
Yeah, we got you.
All
Good
right.
work.
All right, thank you, Carl. As you heard about operation of autonomous machines in shared spaces, I will go over several functional challenges and requirements for these machines to operate in such spaces. So there are different autonomy components necessary for machines to be able to work autonomously in shared spaces. Starting with the knowledge of machines about environment, we cannot assume that a detailed map is available for autonomous machines. And even if one specific map is available, we must account for changes in the environment, including new static and dynamic objects in the space and other machines. SLAM, or simultaneous localization and mapping, is a common approach for an autonomous machine to explore an unknown environment and build a map of explored areas while localizing itself with respect to the environment. Next step is for the map to be provided to a localization package so that the machine localizes itself with respect to this known map. And finally, knowing where we are within the map, the robot should be able to plan its way through the obstacles and reaching its destination. And that is the autonomous navigation component illustrated in this slide. So let me discuss the basics of SLAM here and some of the challenges in this space. The problem of SLAM and creating a consistent map of an unknown environment depends on different factors, including the environment, sensor availability, and computational requirements. Different SLAM techniques exist. As such are particle filter pairing-based algorithms such as G-mapping, and graph optimization-based techniques such as Google Cartographer. And specifically, graph-based optimization methods are very popular for SLAM. And I will talk a little bit about the basic idea behind graph-based optimization. So there are two main components. There is the sensor-dependent processes that basically comprise the front end of the SLAM. Basically, what we do with this sensor-dependent processing is that we estimate the motion of the rover with respect to the environment, and we also estimate the obstacle locations using the sensors and different dead reckoning techniques that exist. And when we have this information, in the back end, which is the sensor-independent processes, we register pose graphs, and we do graph optimization to create a consistent map of the environment. So why the optimization-based techniques are popular? When the amount of data to process becomes too large, graph optimization techniques based on scan matching algorithm become more suitable because they are faster, and when different types of sensor information are fused, such as like LiDAR information, IMU, GPS, and wheel odometry, then this class of methods generate more consistent maps. Loop closure constraints could also be used with this class of techniques to help the consistency of building map of larger spaces. So because these approaches are computationally more suitable for larger areas, and if we can incorporate more sensors, then a more robust map of a larger environment could become feasible. However, a lot more parameters tuning and calibrations are necessary, which is not a trivial task. So here you can see how we basically build a map of the basement of the Noblis headquarters, where Chris and Carl are coming live from, based on a number of sensors that are all prone to drift errors, but are all working together to create a map that looks consistent. This is basically not a trivial task to create a consistent map of a larger GPS-denied environment only based on dead reckoning techniques and local sensors. As you can see, submaps of all the different rooms and hallways are created and correctly patched together as the rover explores and scans new spaces. Lines are parallel and different spaces are patched together nicely, and the overall map looks nice and consistent compared to the actual plan of the building. So for this type of SLAM algorithm, two subsystems work together to produce this map, the local SLAM and the global SLAM. Local SLAM basically generates a series of submaps which are locally consistent but drift over time. And the global SLAM finds loop closure constraints between submaps to produce basically a global consistent map. It executes loop closure by matching scans of sensor data, particularly the LiDAR data, against the submaps. And other sensors such as IMU, odometry, and in some cases, GPS could be used to attempt to get the most consistent global map. Here, when we build a map, we can use it for autonomous navigation. Here is the rover in action using the map we previously created. The map needs to get updates as new static and dynamic obstacles appear so that the rover can plan its trajectory while avoiding new obstacles. It goes through two stages again, the global planning and local planning. In the global planning stage, the navigation algorithm tries to find a collision-free, kinematically feasible path from a start to goal while skipping the differential or dynamic constraints. And this is basically how to plan an optimal path from a start to finish without any collision. It's sometimes the case that the robot perceives itself as a stuck. Then it should perform a recovery behavior, in this case by rotating in place to clear out the space. In the local planning stage, on the other hand, we use path smoothing to meet the differential and dynamic constraints for a shorter horizon and produce the suitable velocity commands for our rover. It could be the case where there is a path in the global map that does not exist anymore because it's either blocked by a new obstacle or there is another machine on the way. So the robot will still need to drive along the path until it can observe the problem and plan around it via the local plan. As you can see, the robot could successfully use the map and autonomously get to its destination. And now we see the rover on its way back from the mailroom here at Noblis to the lab. On the right, you can see the map that we created in a previous stage. The rover is now using the map basically to navigate its way all the way to the lab. And if the parameter tunings are done carefully and successfully, then you can see it can go through narrow spaces such as the lab entrance. So we discussed some of the functional challenges to achieve autonomy of machines. We discussed SLAM for localization and mapping. We briefly discussed autonomous navigation and path planning. And now I will talk about some other challenges that need to be addressed for a more specific use case. Beside the autonomy of individual vehicles, let's see what it takes for a group of autonomous machines to do coordinated searching of an area, trying to find an object of interest and retrieving it. As machines are searching the environment, they need to individually perform SLAM and autonomous localization and navigation. However, they need to coordinate with each other efficiently in building a global map and use this as a reference for their search and recon activities. Moreover, for the use case I just described, the team requires at least one capable machine to manipulate objects and retrieve those objects if necessary. So you see a number of new challenges for a coordinated recon mission, and those are creating a global map, cooperative object detection, classification, and localization, and object manipulation. I will discuss these challenges a bit further in the next slides. So creating a global map of the environment using individual robot maps is another functional challenge when working in a shared space, with multiple machines working as a team to search and map a larger space. This is an active area of research at Noblis where we are testing different techniques for merging 2D occupancy grids and 3D point clouds to create a global map for a team of heterogeneous machines. This problem is also known as a multi-machine SLAM problem, where we leverage the diverse capability of heterogeneous machines to create a global map by merging the local maps built by individual machines via different sensors. One interesting approach we are taking is to merge occupancy grids that are created by different sensors, such as LiDAR and stereo cameras, which can be considered as a multi-machine, multimodal SLAM problem. And other form of maps are also, such as like feature-based maps and topological maps, can also be considered depending on the specific use case. So another challenge area for the example use case presented in previous slides is the ability of the heterogeneous machines to not only detect obstacles for navigation purposes, but also to detect objects of interest, classify them, and also localize them, and then identify those on the global map. The challenges in this area are twofold. One, to implement a framework for fast and near real-time object detection and classification. And second challenge is on how to effectively implement data fusion techniques to benefit from a range of sensors to help us meet our requirement. Here you can see two side-by-side demonstration of LiDAR-based and camera-based object detection and classification, detecting objects of interest in our autonomy lab. So on the left, you see a LiDAR-based basically detection that also localize objects. On the right, you see a camera-based detection. And the overall goal is to be able to fuse these two types of detection together to have a rich detection. So in the use case we described, where a team of machines have created a global map for autonomous navigation and searching, if we successfully detect object of interest, it's now time to approach the object of interest and manipulate it and retrieve it. In this demonstration, we are using a robotic arm with an eye-in-hand camera and visual servoing techniques to detect an object with arbitrary shape, localizing it and sending its pose to the robotic arm for retrieval. In a nutshell, our sensor, in this case, a stereo camera, produced a dense point cloud, which is a 3D point cloud representation of the world. We then downsample our point cloud, apply different filters to have a uniform point cloud, and we do some segmentation to identify a winning cluster, which would be our object of interest, and eventually estimate its pose. The Cartesian pose is then sent to the robotic arm so that the arm can come up with specific optimal join angles for approaching the object of interest and eventually pick it up and deliver it to a desired location. And in this final demonstration, we show how all the described autonomy components are integrated to autonomously explore and map the environment, and then use this map to navigate to the object of interest and retrieving it using the robotic arm. The main difference in this demo compared to the previous one that we demonstrated is that to create the map, the rover is in autonomous exploration mode, where a specific algorithm named frontier-based exploration technique is used to greedily explore the environment, perform SLAM, and create the maps until no frontier could be found. As you can see, the rover is autonomously exploring an unknown plotter environment with all sorts of different objects in the lab space, so that we could actually test the robustness of the localization, navigation, and sensor system in mapping the environment and avoiding obstacles in a random, unknown indoor space. After we finish exploring the environment autonomously and we create the map, it's time to use the map. So as you can see, the rover is basically exploring new spaces, and when it makes sure that there is no more space to explore, it complete the map, and we can then use and also create the map of that space, and then we can use that map to basically retrieve the objects. When the machine arrives at the target position, now the machine is sent to the target position. And when it arrives at that position, the robot will start retrieving the object of interest using the autonomous manipulation techniques we discussed previously. It uses its stereo camera vision sensor to create a 3D point cloud representation of its field of view, apply a number of different pre-processing, processing, and post-processing techniques, including segmentation, to detect the object of interest and localize its center point, and then attempt to reach and pick the object and deliver it where it should be delivered. So this was a brief introduction to several functional challenges, being robust multimodal SLAM, cooperative map creation, sensor fusion for fast object detection, classification, and localization, vision-based adaptive object manipulation, and autonomous exploration of unknown environments. Thank you for listening, and with that, I turn it over back to you, Carl.
Great, awesome. Thank you, Mohammed. I'm going to share my screen again here. So I think a critical thing that Mohammed illustrated there is this capability of the machines to operate independently. And in many cases, map, assign tasks, and then conduct specific and complex tasks associated with the capability of the individual machine. But before we get too sort of thrown into what can the machines do by themselves, remember that they're still doing things for us, right? Humans are the derivers and the generators of the use cases. And in some cases, in many cases, we want to make sure that the humans are included appropriately in the autonomous machine system so that they can interact in an appropriate way at the right level or when needed. And so those requirements are actually quite different. And the ability to manipulate, influence, or otherwise control a relatively large machine team at scale is the topic of our next, I forgot to advance the slide, our next demonstration from James O'Hara. Well, I told you roughly what I was going to say. Here's the slide. But with that, we're going to throw it to James to show how we incorporate human interaction at different kinds of levels into machine teams doing complex tasks. James?
Thank you, Carl. Give me 1 second. First time I tried to share, it didn't share the right thing. Okay, perfect. So as Carl said, our next part is our human and autonomous system interface and engagement. So the way we define human autonomous machine interaction levels, we have 4 different here. We have human in the loop, where the human is performing all the actions, and they're completely in control. There's almost no autonomy there at all. They might have some sensors that provide the human information to how they should act, but there's no autonomous decisions being made. Human on the loop, where automation performs some functions while human monitors and can choose to intervene at any time, and the human still exerts control while still allowing the autonomous system to move on its own at some times. Human over the loop, where the automation performs almost all functions and the human is able to just provide oversight and high-level guidance. The human manages them but does not control. So that's assigning a mission but not a specific task to carry out that mission would be an example. And then finally, human out of the loop, where the automation performs all the functions with human having no awareness or ability to intervene in any way. And the automation has total control under initial authority granted by the human. So what we've been focusing on here at Noblis mostly has been in our middle 2 cases, the human on the loop and human over the loop. So our first demonstration that I'll have for you today is remote monitoring of autonomous machines. So in this case, we'll still have our same 2 small autonomous rovers. They'll be navigating the same constrained space, but we've added additional obstacles as well. The human being will be present in the physical space, but will represent an idea of being in a remote location. And so he'll use only visual and auditory interfaces to monitor the actions and the perception of the machines without any physical identification or vision of what the machines are doing, which you'll see in a second in the video what I'm talking about. So again, as you see, we have on the left, we'll have our 2 fully autonomous rovers. In our bottom right is our human participant, Shihan. He's using our visual and auditory interface. As you can see, the 2 autonomous vehicles are directly behind him. He has no physical way of seeing or knowing what they're doing. He's only using the view that he sees in the top right there of the vehicles moving across the screen. The green bars represent the heat, the obstacle detection that they're performing, and the blue dots represent their intent, the paths that they're planning to move along. So in this way, what we want to prevent is the idea of human out of the loop. If you send out there are a lot of good use cases for remote autonomous vehicles, sending them into dirty, dangerous situations that you don't want to place a human being in. However, if you just send out an autonomous machine team and say, go complete this mission, and then they come back with some data, it's very difficult for you to know, one, what's the reliability of that data? What did the autonomous machine team actually do? Did they actually complete it successfully? So like some of these cases where you saw that yellow rover was stuck by that obstacle for a long time, if we're not observing them directly as they're working, that makes it hard to mitigate situations like that. Or in these other cases where the yellow and the blue rover have gotten a little too close together, we would want a situation where maybe the human being could even directly intervene and control one of those rovers to make sure they can get through and navigate that situation successfully. But even overall, we want to be able to monitor, see how they're collecting the data they're collecting, how they're interacting with the world around them, how they're trying to accomplish these missions. And so our next demonstration, like I mentioned, is the ability to also perform remote intervention and control. So in this case, one vehicle will be autonomous, that'll be the yellow one, and one machine will be remotely controlled by Shihan, that's the blue one. So he'll be able to help the autonomous machine navigate difficult situations before returning to control. So this is a specific example where Shihan will have control of the rover the entire time, but it is illustrative idea where he could monitor an entire autonomous machine team, and then when one of those vehicles has an issue, it could quickly ask for intervention. He could intervene quickly, and then pass control back to the autonomous decision engine, and then wait until another member of the team might need help as well, while still performing the monitoring actions that we saw in the previous demo. So in this demonstration, again, as you can see on the left, you'll see our top-down view of our autonomous yellow rover and human-controlled blue rover. Again, Shihan is in the bottom right. You can see his back is completely to the other two vehicles. He can't see what they're doing. He's only driving using that top right view, which is in the first-person view now. You could see the yellow rover drive through it at the beginning there. And now Shihan is at the goal point and is turning around. One of the other things you'll see is the waypoints moving in front of him, showing where he's tried to get, where the goal point he's trying to get to is. He can also see the waypoints of the other autonomous vehicle in case they're going to be in a close situation. That allows him to maneuver and make sure he's not in the way of the autonomous vehicle, as he's doing right now. He also can see those green bars representing the obstacles so that he knows not to drive into the obstacles. So Shihan is attempting to get to all three of the goal points of the blue rover successfully, all while doing this remotely. He's gotten to 2. As you might also notice, the yellow rover is stuck again because it's gotten too close to the obstacle. So that's another example where you might have some autonomous recovery actions like Mohammed was showing earlier, but in some of these cases, the autonomy engine might not be able to recover. And that's a perfect example of when you'd want the human be able to drive it as well. As you can see, Shihan has reached the 3rd goal point and got to all of them together. So that was working in a situation where you're remotely, but in a lot of other cases, you might be working side by side with an autonomous vehicle. And it's very difficult for human beings to have a shared situational awareness with an autonomous vehicle in the same way that they would with a human being. Even with physical presence, you can't use the same sort of language, gestures, same sort of visual confirmation. You don't know, the way your eyes works fairly similar to the way another human being's eyes work, but they might not work at all similarly to how the sensors on an autonomous vehicle work. So in this case, we have a participant wearing an augmented reality headset, and there'll be one autonomous machine with them in the space using a depth camera to map the area. The participant will need to complete a hands-on activity. It's cup stacking and unstacking, just a representative activity of something that would require total concentration and full attention on his part. He can't be distracted by the world around him, and he needs both of his hands to complete it. The autonomous machine will need to perform reconnaissance and look out for malicious actors, perform mapping, collect data for the human beings that he knows as he's moving through the space that it's safe. And then the participant will use the AR to see what the autonomous machine sees and to give the machine high-level instructions. So this is our CUPS demonstration. So again, we have Shihan. He's now wearing our augmented reality headset. The augmented reality gives him a view of what the autonomous machine is seeing. So the point clouds being generated in 3D by that autonomous machine could be mapped to obstacles, or if you have our other rovers, just those IR heat bars that you saw before, could map where obstacles are and also detect if there's something unexpected in the environment. Shihan, you can see, also just performed a gesture there. In that case, what he was doing is he created a waypoint that he could then place into the world, in the augmented reality world, that then got translated into a real world GPS coordinate that was then sent to the autonomous vehicle. And the autonomous vehicle then knew the goal point of where Shihan wanted it to currently be mapping. So as you can see, Shihan generally sends the vehicle ahead one space, one table to map the environment that he's about to move to see if there's anything interesting there. And then once he's confirmed that he's good with that space, he'll then create a new waypoint and then place it somewhere in the environment. The other benefit that you can see here is that Shihan's able to perform these actions while on the move. One of the issues we've seen with previous in-field systems for human and autonomous machine interaction is that they use fixed screens or tablets that require a person to look down and click through it with their hands. That's a lot of actions that you can't really do on the move. You can't really do suddenly. You kind of only use it for planning, and then once you're in a situation, you stop. The benefits we see with augmented reality is that Shihan can always look up and see what the autonomous vehicle is seeing and doing, quickly interact with it in a very natural manner where he's just creating using gestures to create a waypoint, place it in the world as if he's really putting it in that space. And then the autonomy does the rest of the work to do the mapping for him. So it's a lot easier to do on the move, a lot easier to kind of pay attention to what you're doing. And so one of the other key issues here is making sure that the amount of information presented to Shihan is enough for him to know and be able to make good decisions based on what's being collected by the autonomous machine, but not so much that it's overwhelming, that it's distracting, that it creates an undue burden. What we don't want is him to become fatigued quicker, because not only is he doing this physical task, but then he's doing all of this interaction with the autonomous machine. So that's why we try to unload as many tasks as we can onto the autonomy engine, and we try to make it as simple as possible for Shihan just to get the quick information that he needs, and then he can look away, focus on the physical tasks that he is doing at that time, working with the cups without having to pay any attention to the autonomous vehicle. Like right now, you can see he's clearly paying attention to the cups, making sure he stacks them correctly. And an issue we would see is if we were presenting him too much information and it was overwhelming his field of vision, it would be very difficult for him to be completing this task correctly every single time. So as you can see, you can place the waypoint in a lot of different manners. It's whatever works best for him, whatever works best on the move. And if we were to see a malicious actor suddenly appear behind him, you would see that. So that was the last one that we could see. Our advanced interfaces required for humans and machines to share situational awareness. Interfaces should provide necessary information without distracting the user or increasing fatigue. And interfaces should provide natural, intuitive control structures. And with that, I'll pass it back to you, Carl.
Awesome. Thank you, James. I always enjoy watching Shihan do the cup stacking while he's trying to control the rover. That's always a really good one to show off some of the complexities, even a relatively simple environment, of having humans and machines, autonomous machines, together. Okay, so now I think the moment we've all been waiting for is to get to our distinguished panel discussion. Chris and I will be doing some of the moderation here on that, but we're not as important, of course, as our esteemed panelists, so I'm going to jump forward a slide here. Talk a little bit, and I'm going to throw it to each of our panelists so they can introduce themselves a little bit better. Just to let you guys know who are joining us as participants, we can take a few questions. I noticed I was trying to answer one or two of them in the chat as we went along. We may not be able to take all the questions for our panelists that come in today, but if you do have some and you want to use our chat function here in WebEx, we will try to include them as best we can. It's really going to be a limitation of my ability to manage multiple screens at one time to make that happen. But without further ado, I would just like to introduce our panel in order here. And I'll start with Andy Lacker, who is the Chief Technologist for Future Airspace Operations, Intelligent Flight Systems at the NASA Langley Research Center. So I'll just do a quick audio check. Andy, are you out there? And if you are, can you jump in and tell us a little bit about your work and experience in the field of autonomy and emerging technologies?
Sure. I'm assuming you can hear me, correct?
Yeah, I can hear you. Great, thank you, Andy.
Okay,
Oh, now I
great.
can see you too, so that's even better.
Okay, well, I'm an aerospace systems engineer. I've had a varied career. The last 20 years or so has been focused on the safety, security, and operational integration of unmanned and autonomous systems. I've worked most of my career from a government perspective, including 30 years at MITRE, a short stint at Noblis, as well as a bit of time on the commercial side working at Boeing and a couple of airlines. Right now, I'm a NASA federal employee where I work looking to the future of how we are going to enable unmanned and autonomous systems, as well as other new aviation technologies, function in future airspace. And I'm based at Langley Research Center in Hampton, Virginia, in the Intelligent Flight Systems Research Directorate.
Awesome, thank you, Andy. Great stuff, and it's great to see you again. Moving on to our next panelist, sort of from the left to the right, is my client, Kate Hartman, from the ITS Joint Program Office at the U.S. Department of Transportation, where she's the Chief of Research, Evaluation, and Program Management. So Kate has a quick audio check. I just see if you can jump in and tell us a little bit more about yourself, your background, and where you think you fit in sort of this world of getting merging technologies into widespread operations or integrating it with mainstream operations. Kate?
Hey, thanks, Carl. I appreciate that. Hi, everyone. I'm Kate Hartman, as Carl said. I am with the U.S. Department of Transportation in their ITS Joint Program Office, where we do a lot of the department's coordination on intelligent transportation systems for the transportation network. And that involves working with all the modes, pretty much very little with FAA. So we're really looking at landside type vehicles and a little bit of work at the ports. Most recently, I have been working in the connected vehicle space, and we're just finishing up large-scale pilots in New York, Wyoming, and Tampa. I am currently serving as the AV program manager. We had a retirement and are furiously trying to find a replacement, but it's the intersection of connected and automated, and it's been an interesting ride going through that. So looking forward to the panel.
Awesome. Thanks so much, Kate. Next on my screen here, we're going to move over to Dr. Khan Azbeh, who joins us. He's a professor at the Department of Civil and Urban Engineering and the Center for Urban Sciences at New York University, but he's also somebody I've known for maybe 30 years. So Khan, if you want to jump in, we'll do a quick audio check and tell us a little bit about yourself and some of the work you're doing in the world of getting autonomous machines at scale of working in an urban environment. Khan?
Yeah, thank you, Carl. I hope you can hear me well. So I'm Khan Azbeh, and I'm a professor at New York University, Department of Civil and Urban Engineering, as Carl said. I'm also the director of the UTC Tier 1 C2 Smart, where we really focus on urban problems from a big data and other AI kind of perspectives. So my interest with actually autonomous systems started many years ago with the funding that we received from FTA and looking at how we can automate buses, obviously in the simulation, using the XPR dedicated bus lane on Lincoln Tunnel, and what kind of improvements we can get. And then we did the study, we kind of showed that in the simulation, you could really get 25% of flow improvements when you had these kind of autonomous buses. So, and then as time went on, we worked on these problems and really trying to understand what we could do in terms of automation and connected vehicles. They go hand in hand in big cities. And then we actually completed, in collaboration with New York City DOT, one of the largest field deployments, New York City pilot test for connected vehicles. And then actually, it was a great experience. We learned a lot. As usual, these kind of technologies, they work great on the simulation, but that field work is always a challenge. And we hope that we can use some of that knowledge to kind of take the autonomous and automated vehicle technologies to the next stage, basically deployment and not really large scale, but first limited, then large scale deployment, and see how we can improve the transportation system. So I hope that gives an idea about the things that we are interested in doing.
Awesome, great. Thanks, Khan. Our last panelist here is someone I just met, Greg Hayes, who I believe may be joining us from South Carolina today. I believe he's located in Charleston with the U.S. Navy at Niewek Atlantic. Greg is the Director of Rapid Prototyping and Experimentation. So Greg, I don't know if you can just jump into a quick audio check here and tell us a little bit about your work with autonomous systems and some of your experience. Greg?
Yeah, will do. Thanks, Carl. Good afternoon. As Carl said, I'm with the United States Navy. I have about 20 years in the government and about 12 on the outside, sort of in between that, pushing a lot of disruptive technology and rapid response type of opportunities. So in my job, I have what's called sort of speed to mission, where I try to rapidly go out and identify, adapt, and implement new technologies and capabilities faster than our adversaries. I'm currently putting autonomous systems in what I call real-world experiments. This big blue thing behind me here is a huge playground that we do a lot of autonomy testing in. We do some of it in international waters. It gives us a little bit more flexibility for doing some testing. But I'm also, quickly realizing that it's really not necessarily a technology challenge for the most part. It's the culture around all the aspects of autonomy and kind of how that plays into, one is the traditional way we acquire and partner with industry, but also just the legality and some of the missions that we do in the Navy, trying to have that level of trust that we mentioned earlier. So I do have a lot of appreciation for the commercial sector. There's a lot of techniques and opportunities out there now to try to bring in the autonomy technology and the AI and machine learning pieces to realize that the quicker we can get it in our environment, and our environment is quite a bit different because we don't always have connectivity guaranteed. We don't always have the ability to have reach back to the cloud. We don't have the ability to use the traditional radio frequency, Wi-Fi, cellular type of linkages. So that offers a lot of disruption. But we wanted to try to get the technology out in our environment so we can essentially make it smarter, right? Because autonomy is only as good as the environment that it's in. So the sooner we field it, the sooner we get it out and experiment, the smarter the systems become, and then it starts changing the way we utilize those. So I look forward to the questions. Thank you.
Awesome, thanks, Greg. I think just from the introductions, it's clear how much interest there is in autonomy, in these emerging technologies, and trying to grab hold of some of those opportunities by deploying operationally. But it's just not an easy walk to get there. We have a few kickoff questions here. I'm going to move through them as the sort of our starter for today. The first one is for Andy. So Andy, your kickoff question is, so NASA is a leader in autonomous systems, given the nature of managing operations distant from human control. So when you think of autonomous operations in close proximity to humans, what topics are critical to understand and ensure are working correctly? So Andy, if you want to jump in, and after Andy has his remarks, we ask the panels to jump in as well if there's anything that they'd like to talk about. But for right now, we'll throw it to Andy for his response.
Yeah, my focus is on aviation in a civil context. And when you fly in the national airspace as a civil aircraft, you're integrating, if it's an autonomous flight, you're going to be in and around other flights that may not be operating under autonomy. They may be operated by a pilot, they may be flown remotely. And you have to find a way to coexist with these incumbent operators in the system. And I like what Greg said about, it's not always the technical challenges which are the hardest. Some of them are the policy and procedural and operational challenges associated with integrating these aircraft into a single operation. And so when you think about aircraft that are flown without a pilot, that are flown where software effectively is the pilot, how is that aircraft going to follow the rules of the airspace? You know, most of us are drivers, and we can imagine driving a car. Well, if we're going to have a driverless car, the driverless car has to drive on the same road with me driving a car. Well, in aviation, we have the same challenge. We have an autonomous aircraft has to fly with others. And the other challenge that we have is, because we can take the pilot out of the aircraft, we can make aircraft that are really small and that could be flying and doing missions where we don't currently have aircraft flying today. We basically expand what we can consider as navigable airspace. And that means we are potentially putting aircraft in close proximity to people who are not aviation trained. So today, you know, the airport area is tightly controlled, and the only people who walk on an airport tarmac are people who are authorized to walk on an airport tarmac. But now the airport can be everywhere. You know, we can have aircraft that can basically land anywhere. And that creates new challenges, including, you know, if an aircraft is now delivering packages to my driveway, how are the little kids in the neighborhood and the dogs going to respond to that aircraft? And how are we going to make sure that that operation is still safe? And so those are some of the challenges at NASA that we're looking at as we look at autonomous flight. How does this autonomous flight fit in to the rest of aviation, and how do we ensure that it continues to be safe?
Yeah, great point, Andy. I look forward to having aircraft land in my driveway. I think there's just enough room there for me to get back and forth to work, so I appreciate that. And I would also like it not to hurt me or my neighbors, so I 100% get that. I guess ask if there's a follow-up, any follow-up question on that particular, any other comment from our panelists, or I've also throw it to Chris here. If you guys have a follow-up on the notion, not just on Andy's landing his autonomous aircraft on my driveway, but anything else related to the humans, you know, the human mixed environment with the autonomous machines. So I'll just.
So Carl, I'm going to jump in since Andy mentioned driving
for
cars. Yeah, so it sounds like we've got a lot of similar issues, and you know, how long is it going to take to get a fleet turnover? You know, is just one thing, but then how do you address the timing and how they interact? And you know, if they are truly autonomous, are they really, you know, looking out for? I assume they're looking out for themselves, which may not be looking out for the system as a whole. And is that something we want to do? And if you're trying to optimize for the system, you're going to want some kind of connectivity. And, you know, we've been working on that. But as you said, you know, as Greg said, the challenge isn't the technology. For us, we call it the institutional issues, because we've got 50 states with MPOs and individual cities. And then we've got car manufacturers. And then we've got regulatory bodies within the department. So yeah, it's a challenge. So glad we're not alone in it.
Right on. Yeah, that's part of what we thought we might have this session, because we thought there would be some connectivity. So thank you so much, Kate, for your observations. I'm going to jump forward to our next kickoff question. This one's for Greg. So Greg, get ready. It's kind of a long question, so I guess you got some time to think about it. Recent events in Ukraine and elsewhere have generated a lot of press related to unmanned drones as tip-of-spear kinetic applications in the battle space. What are your thoughts on the potential value of autonomous systems in these situations versus, let's say, more prosaic logistical functions related to things like recon, refuel, resupply, and maintenance? Greg?
Sure, that's a great question. There is no doubt that commercial technology is changing the way we fight the war. I mean, even outside of the unmanned, but things like the SpaceX's Starlink, you know, rapid deployment, and then also the rapid updating to counter the Russian jamming was a testament to just how thriving our innovation ecosystem really is in the United States. As far as the drones, I mean, we're seeing a lot of press now from, like, the Switchblades or the Phoenix Ghost. There's no doubt. I mean, the bombs and bullets is what gets the press and what gets the Congress excited and a lot of resources. But I think any military expert will tell you that it's logistics that win the war, right? So our ability to deploy, replenish, and sustain forces will actually, you know, is what usually determines the outcome. So in the Department of Defense, we use the terms like contested logistics or resilient logistics, and it's the ability to looking for unmanned solutions and autonomy to expand our operational reach, trying to find ways where we can deliver fuel, munitions, and other material where we need it and when we need it. And a lot of it is in harm's way. So it's a lot of the same challenges I mentioned earlier about you don't have connectivity guaranteed. You don't have the ability to replenish close by. You don't have the ability. So there's a lot of challenges out there, and what we're trying to do now is play those scenarios out and see you know, how that really does change. Because, for example, unmanned vehicles on the ocean, at some point they got to refuel, right? So right now when two ships refuel at sea, I mean, we sort of have to turn off all of our gear when we do this sort of dance between two manned vessels. And if one's unmanned, it's kind of hard to do that. So trying to get to true relative position, you know, to close launch and recovery and things like that continue to be a challenge. But it's the logistics side that's starting to put a lot of energy in that area. So in the Navy, we have we just set up the unmanned campaign framework. It's publicly available. It released last year. It talks about the levels of autonomy. It talks about from the human being in the loop all the way to true autonomy and some of the attributes of that. And then we also are starting to do some experiments in this area with we just got one with the Office of Naval Research down in JIDA South, which is in Key West, that does all the southern drug proliferation and illegal trafficking challenges. It makes for a very good experiment because you're not necessarily firing any weapons. So you can do a lot of logistics type of scenarios and try to go after the big data challenges and the unmanned areas that's very real world scenarios that could be then applied to sort of something, say, in theater. Over.
All right, so Chris has got a question. Chris, you want to follow up?
Just a quick follow-up. Thank you, Greg. Just curious what the level of coordination is between the services that you're seeing so far in autonomous systems, in the frameworks and the technologies and joint operations. Comment on that briefly.
Yeah, Chris, can you repeat that, or Carl? I couldn't hear him.
Well, I don't know. Maybe Chris might be muted. Are you back on, Chris? I don't want you to go ahead.
Can you hear me, Greg?
I can hear Carl really well. I can't hardly hear Chris.
All right, I'll reformulate that. I'll see how well I listen to Chris. I'll try to say his question for you. All right, so the question was, so that's great stuff that the Navy's doing. Do you see a lot of connectivity with your other parts of the military, other services? Are they, is there, in terms of a common framework, Navy, are you working together with the other parts of the services, Army and so forth, to manage autonomy in an effective way, or is it pretty much Navy's got its own set of problems and you're working on those?
No, we do. It's a lot of it's in the experiment venue where joint capability demonstrations and these other things that have a lot of cross-service, a lot of priorities being placed in cross-service type unmanned experiments to do exactly that. We also got a good bit of international. We had a big international experiment in February over in the Bahrain Gulf area called the International Maritime Experiment, IMX 22. It had a lot of different countries because there's a lot of unmanned autonomous technology going on globally that is pretty impressive as well. So to bring them into the mix is pretty powerful too. Thank you. Good question.
Great. Thank you.
Thank you.
We'll make sure we get Chris's mic fixed over here so he can ask questions. Can't always pass it through me. All right. Our next kickoff question is for Kate. Kate, nearly every vehicle sold in 2021 had some form of wireless connectivity as well as augmented driver support, ranging from things like blind spot warning to automated lane changing. So are our roadways already autonomous systems, or are key technologies like wireless connectivity still evolving? Kate?
Well, the short answer is it's still evolving. The longer answer is if you consider a person to be able to control an autonomous a vehicle, then every vehicle right now is autonomous. But if you mean machine control, we're not quite there yet. I like to tell the story. I had a family member get recently purchased a new car, and we could talk about the supply chain and how long all the issues that influence that and how autonomy may be able to help. But anyhow, they bought the car and they were all excited to tell me about they got almost an automated vehicle. It had all these cool features on it. And as he started telling me, I was like, it's not automated. You still have to be in the car. You still have to control it. And the things that you're talking about nowhere close to where the technology it can take you. So I think there is some misperception by folks about what exactly an autonomous or an automated vehicle can be and will be, but there's been a lot of hype and a lot of press in the last few years about we're ready to bring it. We've got one relatively new OEM that has been at the head of the hype cycle. So there is a lot of misinformation, and there is still, a lot of work to be done, especially in the connectivity part, if that's going to happen. So that's where we stand right now.
Yeah, great answer, Kate. And I'd have to say, people have seen a lot of autonomy in CGI in movies, and they think that's the world they live in, right? But the reality is somewhere in between. I don't know if there's anybody else. I think Andy was about to jump through the screen. Yeah, I was going to say on this topic. If Andy, you want to tell us a little bit about some of your thoughts about this? Go ahead, Andy.
Well, we have a really nice current event to give an example. In aviation, we've had autopilot and auto throttle for years. Doesn't mean aircraft are autonomous. You need the pilot to set those features, and those features don't get you to land. So yesterday, coincidentally, we had an aircraft that had a pilot who became incapacitated, and a passenger took over the aircraft, and with coaching from someone on the ground was able to land that aircraft. That aircraft had auto throttle and autopilot on it, but you needed the passenger with tremendously excellent coaching from the ground to be able to land that aircraft. And that was quite a miracle, to be quite frank. But we don't have autonomous aircraft. Now, there is a feature that has been recently certified by the FAA as a backup emergency feature in the case of a disabled pilot, an incapacitated pilot. There is a system that you can press a button, essentially, and the aircraft will choose an appropriate airport to land in and head to that airport and do the radio calls and everything that's necessary to land in an emergency fashion. And for that circumstance, in an emergency, you have an autonomous aircraft. But that's a brand new system, and it's only available, I believe, on 2 aircraft models. And I don't even know how many are actually deployed, how many individual systems are actually deployed in the field. The aircraft that was in the incident yesterday did not have that system on board. But it was what it was created for.
Yeah, and to be clear, there are automated vehicles out there that have been in some limited piloting and demonstrations, but they are by no means anything that you can go to your local car dealer and purchase today. So it sounds like similar.
Car dealer, have it drive home for you. We're not there yet. Although some people I talk to that are owners of certain kinds of cars believe that they can, but they have not successfully done it. Great. Our last of our kickoff questions. We'll come back to this one, I think, Greg. I think that the whole question of where are we really in autonomy is going to color the rest of the conversation for sure. But we'll wrap up our final kickoff question with Khan up in New York. So Khan, your question is, from the perspective of a resident and researcher in New York City, considering the introduction of increasingly automated vehicles, taxis, buses, and delivery drones, what do you see as the most important potential impacts on human behavior and the resulting change to the urban environment itself? Khan? Oh, Khan may be on mute. I don't hear him. Kate, can you hear Khan? I don't think I hear him.
I can.
Good,
He's on mute.
All right, good.
Sorry. Okay, great. We got it. Thank you.
I was trying to. So, I mean, what I was saying is it's a loaded question. It's a lot of assumptions that human behavior changes independent of everything else. In our business, obviously, in transportation, human behavior is really affected by so many things. And actually, there's a wonderful book by Marvin Manheim that I use in my class, Fundamentals of Transportation Systems, where he kind of puts together different components, different things that affect human behavior in terms of travel. And of course, I think if I want to summarize what I get from this question is that, how the human behavior will change is basically due to the availability of this technology. So we talked about it, everybody mentioned, if the technology is already available, we might think that it's available, but it might not be. And what is the full cost of that technology? It's not just purchasing, but operating and maintaining and so on. So, I mean, we just need to think about these things when we think about human behavior and its impacts. I think a couple of things I can say about individual impacts. That means just people who are commuting. If you have a fully autonomous system of vehicles, trip-making decisions will change, definitely. Probably people will take longer trips, the parking behavior will change, and so on. I believe that, and some people might disagree with me, the safety will change. The system will become safer because we will eliminate human errors. As a result of these two things, I think the land use will change. So I'm thinking like a big picture. So the way people, where they live, how they choose to, locate their houses will change. And as a result, maybe it's not a good thing. I think vehicle mass travel might change if you have fully autonomous system. But I think we also need to think about from the perspective of freight, trucks, and so on, because I think in terms of freight, it will have huge impacts on operational aspects of freight. So we might be able to operate, for example, longer hours, off hours, and so on. So there'll be a better capacity use of the system because you don't need human drivers. On the other hand, there might be some negative impacts, which we talk about it in New York City. There'll be higher barriers to entry by mom and pop type of companies. These trucking companies, actually, a lot of them are mom and pop, so you can buy a truck and then start your own company. But if it's an autonomous truck, I think it'll be a more centralized system. Big companies might become the dominant players. And then there might be new submodes of freight, like for last mile deliveries, drones, and maybe a more improved logistical system of trip chaining and so on. So just to summarize, I think it might have this autonomous level 4, level 5 type of autonomy might have positive improvements in terms of safety, capacity, in many cases, and there might be less traffic congestion because there might be less accidents and so on. But it might also some unexpected impacts of even employment, of how the trucking companies evolve and how people live. They might live further away from the cities, so urbanization will be affected. So there will be, super far away suburban locations. So I think, one couple of few points. I think the robustness and the cost of autonomous systems will dictate the success or adoption of these technologies. Probably you need a killer app, like something like will take over. It will impact everybody's perception about the systems. I don't know what is that killer app, but probably you need that. But in any case, the adoption of this technology will be slower and incremental. And not only due to the technology, but also the policymakers, lawmakers, because I talked to local DOT, for example. They don't know what to expect when you have 10% of the vehicles are autonomous. Just they're not ready to write the law to regulate them. It's different than just doing some pilots. And then, this is again, I don't know. I was thinking about it. The breakthrough probably in terms of widespread use of these fully autonomous vehicles might come from outside the US. And a good example of that, cell phones. Cell phones, actually, if you remember, was not very widely used, especially smartphones, for a long time in the US. When you traveled to Asia, to Europe, you saw more people using these cell phones, and then all of a sudden it picked up in the US also, and then became very widely used. So maybe it might come from Europe. We know, for example, they're pushing the autonomous trucks very heavily because of labor concerns and safety concerns. I don't know. Maybe that might be the killer app coming from an outside location of the U.S. That's just a couple of ideas.
Awesome. Thank you, Khan. I don't know if there's anybody has a follow-up on Khan's response there or any change to the urban forum. Chris, you okay?
Yeah, the question I would have, you can hear me, Khan. Carl, repeat it. But when you look, when you look at the municipalities and the cities, kind of similar to the answer to Greg, where do we see some significant cities, municipalities taking the lead, taking some of those first steps? You see that in New York City amongst deployment of autonomous vehicles or pilots, or are we just not there yet?
I think New York City is very careful about separating connected vehicles from autonomous vehicles. So New York City is perfectly all right, as far as I know, with connected vehicles. But when it comes to autonomous vehicles, I don't think they're ready for it. Many cities might be doing some low-level testing, but I don't know any city who's really ready to go full-fledged for autonomy.
All right, great. Thank you, Khan. All right, so those are our initial questions. Now we'll move into some toss-ups. So I'll actually, for our panelists, I can see you very well on my little screen here. So if you feel like you want to answer the question after I throw it out there, just raise your hand. I'll throw it to you. It's the simplest of way of signaling human intent, I think, since the dawn of time. Machines have a hard time understanding that, but we know each other, right? We evolved together as humans. So we're going to use that mechanism of coordination here. Just raise your. You don't have to do any of the other functions in chat. Just raise your hand, and I'll throw it to you. All right. So question number one, a toss-up. So one way of engineering a way out of multi-machine coordination is to create purpose-built teams or templates for specific situations. But the weakness, as James pointed out, is that these lack flexibility. So, but any insights on where ad hoc coordination is absolutely needed? I don't know. Oh, Greg is a taker for that one. Go ahead, Greg.
Yeah, so in the military, we sort of call these swarms, right? And there's a lot of offensive and defensive advantages of doing that. And you have a lot of challenges with sense and avoid and coordination, but they offer the ability to reach into this environment that I mentioned earlier that's sometimes disconnected and very challenging, because they can sort of breadcrumb their way in, or sort of ad hoc exchange data and process on the edge, and allow the ability to tie in multiple sensors, potentially decoys and things like that, to sort of overwhelm potential enemy with a lot of very clever small very affordable assets.
Great. Andy's got his pen up. Andy, go ahead.
There's a hand attached to my pen. I think anytime you have a human-centered system that you're going to have to interact with, you're going to need ad hoc coordination. And because humans, just by our very nature, behave in a way that is not always 100% predictable. And so you're going to need systems that are robust to the unpredictable nature of human actions.
Yeah, right on, Andy. In that one, I'll just throw in that, so we've also experimented, just like what James was talking about, establishing a trust score for machines. So machines and humans can also accumulate and earn trust in similar ways, although how it's interpreted is by human and machines are very different. So a common language of multi-machine trust is also important for even making the ad hoc coordination stuff work safely and effectively. All right, no other. Oh, Kate's got her hand up. Kate, go ahead.
Yeah, I'm going to throw out the weather is an ad hoc player on the transportation, and I'm sure with the other folks here. And so trying to get spot weather warnings in order to reroute folks, or a wind gust that blows over an 18-wheeler that causes a crash, and you want to get the information back further so that people can divert, or the system. So there are things other than just humans that don't always follow particular patterns. So that's another challenge that we're looking at.
That's right. Yeah, humans are like the weather in that regard for sure. Thank you, Kate. All right, I'm going to jump to our next toss-up question. I'm going to use this one. So many connected autonomous machines present an inviting cyber target. Compromise one machine and use that to infiltrate the entire system. So for any of you guys, as a toss-up here, what are your thoughts on making autonomous systems more cyber secure? I know Kate would like to take this one.
I'm chomping at the bit on this one. Yeah, and we have actually worked with this a lot in the connected vehicle world with the security credential management system, which isn't always considered to be a cyber solution, but it really is, because it's verifying and checking who can talk to who, and if they're actually who they say they are. We've even gone as far as doing some misbehavior detection to try and probe in to see what happens if you do crack in. So yes, it's very important. It's something we care about. I won't even get into larger traffic management systems, and as states and localities need to control their roadways, there's a whole huge other area for a cyber attack.
Awesome. Any other takers on the panel for the cyber question? All right. If not, I'm going to move on to our next one. Thank you, Kate. Our next question is, the community often talks about ensuring trustworthy autonomy, but what does that mean in a practical sense? Andy, go ahead.
Well, in aviation, our systems have to be certified before they can operate. And so there is a formalized step that the aircraft and the systems on board the aircraft have to go through to demonstrate that the system as a whole is trustworthy. And if it's an autonomous system, it's going to have to go through that same process. And the process for software relies heavily on a development assurance approach, where the process of developing the software is scrutinized. And that approach does not really embrace non-deterministic systems. And as you go to an autonomous system that has to behave in all of these complex environments and deal with ad hoc coordination, et cetera, you're often going to have non-deterministic approaches in your software. And it makes it really difficult to certify. And so one of the areas that the aviation community, including NASA, is looking at right now is how do you do what we're calling autonomy assurance, or how do you develop the assurance case associated with an autonomous system as a step toward the certification process. And so it's that certificate. We have a formalized process, but we have to come up with the techniques to be able to demonstrate that our systems meet the standard. And a lot of that has to do with the purpose of the design system. Now, I gave the example of an emergency autoland system that is autonomous. The FAA was able to certify that system because it's only used when basically the aircraft is lost anyway. And it's a pure safety net that it doesn't have to be perfect, but it has to be better than certain catastrophic event occurring. And so the FAA is taking a step by certifying this system to be used. And the thing that they focused on is that it won't accidentally behave when everything is fine. That was the main thing, was that it didn't kick off when it wasn't needed. And as long as it behaves itself when everything is going well, it is considered good enough, and it uses AI and machine learning techniques, for example, to select an appropriate airport. No one knows ahead of time what airport it's going to select as its emergency landing point. It's going to pick the best available based on a set of criteria, and circumstances would determine it. So anyway, that's the one approach that the aviation community is pursuing. Great.
Thank you. Greg's got his hand up. Greg, take it away.
Yeah, I just want to echo what Andy was saying. I mean, in the Department of Defense, it's the same way. I mean, it ends up being a risk proposition discussion. So if the benefit outweighs the consequences, in that scenario like you just gave, that's exactly in a way that's sort of a crawl, walk, runway approach, because you assume that the more we get comfortable with that, the more we're going to sort of stretch that risk a little bit. And then, even in like the experiments we're doing now, we're probably doing things that we'll never do, at least for years, but it allows the ability to develop that trust and, with the operator and with the machines themselves. Over.
Great. Thanks, Greg. All right, so I'm going to jump to one last toss-up question before we go into our lightning round. That the panels know what that means, where we do a quick question where each panelist gives a short answer to it. But this one's the last of our toss-up, and it's the one that I get the most frequently, honestly, from people who've just watched the movie Terminator. So how do you see keeping humans, quote, in control of these systems at the most extreme level? How can we keep from building Skynet? So that's definitely a Terminator reference. Or more practically, how can we avoid negative unintended outcomes? So any takers out there for the Terminator fans?
I think I can say a few things in what we do.
Sure.
When we, for example, design algorithms for autonomous driving, we put some constraints. So things that they can do, they cannot do. So we constrain the solution space so that the control algorithm doesn't go berserk and then doesn't start doing unsafe things. So it kind of, basically we call it making it robust to things that are going on. Obviously that reduces efficiency, but that's kind of a trade-off between safety and efficiency. And then we try to design algorithms to do that. Is it 100% bulletproof? It's not, but it really reduces unsafe behavior at the design level. Then obviously you have to go and test it in the real world and how it works. Maybe add some other heuristics like Asimov's iRobot, like thou shalt not hurt a human being, or thou shalt not kill a human being, something like that. You can put some heuristics, but also at the design level, you can build algorithms that are relatively safe in terms of operations.
Great. Thank you, Khan. All right, so with that, I'm going to move on to our toss-up section. As I explained just a little bit before, this is just a quick response from each of the panelists. I don't know exactly what the right amount of time is, but in some cases we'll just ask you for an integer score. That's the last one. But one actually is one that Andy suggested. I'm gonna throw it out as our first one, which is, what is one myth about autonomous systems that you wish could be refuted? So I don't know if there's a quick answer to that one, but if you have a short answer, or I'll make that the last toss-up. If you want to raise your hand, that's fine. About the myth. I think we talked a little bit before about the folks with the cars that think they can drive themselves. Go ahead, Andy.
One myth is that autonomous systems don't involve humans. Humans are always involved,
Sure.
and their role may change. They may move from a direct control role to a management role or an oversight role, but humans are involved, and humans are still accountable for the behavior of the systems that they've authorized to do something. And so, you can delegate the responsibility for the action to the software and the automation, but the accountability of what happens when you turned it on still rests with you when you turn it on. And so that's a myth in my mind.
I think one myth that very quickly, they will happen next year. I've been working with autonomous vehicles since 1994 on a US DOT project, actually, when I was a PhD student, and they were saying the same thing. In 2 years, we'll have a completely automated vehicle system. It's not going to happen next year. I think that's the biggest myth, probably.
I'm going to take a twist on Khan's myth, which is they're here now. There are versions of automated autonomous vehicles, but they are not here for you to buy. So kind of my mantra. I mean, we hope we're getting there, but yeah, that car that you bought that the dealer claimed was an automated vehicle is not.
All right, Greg, you got a myth for us?
Yeah, I think internally our culture is that we're going to sort of buy it off the shelf and it's going to work, right? And I think in reality we realize that we sort of have to sort of raise it and grow it because it's got to get used to our environment in order to actually be, smart and productive. So it's almost an opposite of the way we currently acquire technology and solutions. So that's something we have to overcome.
Right on. Yep. Real world is messy. Requires a lot of adaptation. All right. So for we will do the lightning round here now with the quick one on the scale of 1 to 5. 1 being almost no progress, and 5 is nearly all progress has already been made. Where are we in your domain in realizing autonomous systems and the potential benefits? So we'll go in reverse order. Greg, gave us the last myth. So on a scale of 1 to 5, in your domain, 1 being no progress, 5 being all progress already made, where do you see autonomy and being the potential benefits being realized?
I would like to say just a 2, and that's obviously just my opinion. I think we have a ton of opportunity to go, but I think right now we're sort of we're sort of crawling right now.
Right. Yeah. So pretty low score. How about you, Kate? 1 to 5. Where do you feel like the connected automated vehicle world is in terms of its top end benefits?
I'm known as a tough grader, and I'm 1.5.
Okay, yeah.
It's not progress, but we got a long way to go.
Explained about the number of significant digits allowed in the response. Well, 1.5 is totally appropriate. That's great. Thank you, Kate. Khan, how about you? In terms of the world that you look out the window and see, where are we in terms of autonomous systems?
I think we are 2.5 or 3. But that 2, that remaining 2 is bigger than that 3. So it's like, I want to be an optimist, but I think that it's a nonlinear function. Going 0 to 3 is not maybe that difficult, but 3 to 4 will take longer time. So I'm looking at it as a nonlinear system.
Awesome, great, thank you. And Andy, where do we fall on your scale?
Now you asked for an integer answer, and we had 2 non-integer answers. We don't have rule followers here. But I noticed that we're all what might be interpreted as pessimistic. I'm kind of falling in the 1.5 camp, by the way. It may sound like we're pessimistic, but I think just the opposite. I think we're optimistic. I think we see, while we've come very far, I think we all see a great potential ahead of us in terms of what we still could do with this technology and the capabilities that we can still unleash. Now, how fast are we going to get there? I'm not sure, but I'm optimistic that there's much more to be done, and much more benefit to be realized.
Right on.
I mean,
yeah,
Carl,
I think
if you allow me, I want to say something because I give this example. I mean, I don't know. We are all we will remember. The younger students will not. There was something called Apple Newton. It was like an iPad. And I bought that. I could never use it. And then my wife gave me a very hard time for spending all that money and not being able. It didn't work. And then now, so there's a right time for certain technology to work. Maybe one thing, maybe wireless. I mean, I'm not an expert in iPad, but then iPad works for everybody. Everybody has iPad, but Apple Newton, although it's very similar, never worked. So I think the right time, right technology mix, and right population, whatever, I mean, makes that work. So I think it's not that straightforward, just having the best car and then it will work all of a sudden overnight. So I think that's kind of the example I give to my students, so.
Awesome. Thanks, guys. Well, I think we're getting close to wrap up here. I do want to reward Chuck Bristow, who's been putting some comments in the chat here. I would like to maybe throw one last toss-up question at our panel before we call it a day here from the Noblis Autonomous Systems Lab. So I'll read his question. I think the first one may be the most salient for this group. Chuck asks about the safe and effective operation when the autonomous machine is less than 100% capable. So that is a car with a loose wheel or a UAV with a faulty GPS. I mean, machines deployed in the world are not going to be perfect, just like people, right? Andy said people are unpredictable, but machines can also be unpredictable. So I just know if anybody would like to raise your hand if you'd like to take a question on managing machines that may not be acting like they ought to be or may be damaged. Go ahead, Andy.
From an aviation standpoint, that is the hard part. Making the aircraft fly when everything's going fine is not as complex as being able to deal with all of the potential off-nominal, even minor off-nominal situations that may occur, whether it be degradation in the GPS signal or whether it be a faulty rotor. Whatever it may be, you always have to be able to deal with the off-nominal situation. And so it's just like programming, data analysis. It's dealing with the exceptions is the large part of what the programming is involved with. Well, dealing with autonomy, it's dealing with the exceptions in the environment and in the circumstances that requires the most work, and being able to demonstrate that you can respond appropriately in all of these situations is the key.
Awesome. Thank you, Andy. Well, I see we're at 4:25. I did want to make a moment to see if Chris has any thoughts in terms of a wrap up before we thank our panelists and let them get back to solving all these problems. I will say though, real quick, is that my hypothesis going in was that you guys would have something to talk about with each other. So I feel like as an experimentalist, the hypothesis was supported. I'll do the statistical analysis afterwards and report the significance. But that's my observation for today.
Yeah, I think your assessment there and your hypothesis vindicated, Carl, in terms of getting the group together to talk about some very interesting trends and issues in the space. I mean, I think fairly blunt, feedback in terms of kind of where we are and where we need to go. So I think just wanted to say thank you to our panel. Really appreciate your thoughts and insights and sharing those with us today. So.
Right on. And to close out here, I just also like to add my thanks to Chris's. I really appreciate our panelists, also the participants who've been joining us remotely and asking questions. Thank you for your active participation. And as a closing just remark, if you're interested in some of the stuff we've been doing here at Noblis, please visit our Noblis Autonomy website. You can just search for Noblis and Autonomy. You will find it. Some of the videos that we showed today and others are there. There's more information on, again, our worldview and why we think it's important. Again, a key thing that I think folks have said is in some ways it's not the technology. It's setting up the rule sets for these machines and humans to work together more effectively. And I think that's going to take everybody, not just the folks in our lab, but across all these domains to make it happen if we're going to realize the tremendous benefits that I think we're going to get from operational deployment of a large-scale, resilient, self-organizing, reconfigurable autonomous systems. And with that, I'm going to stop my monologue. Thank you, Chris. Thank everybody in the room here for making this happen. Thank our panelists, and thanks our participants. So have a great day. We look forward to getting together with you virtually otherwise in the future. Have a great day.